Alright, so this is the January 2013 Unit 2 paper on mechanics, materials and waves. We're going to start off with some mechanics and we're going to start with some energy. So we've got a world record dive, which is at 54 meters is the world record height, and we want to calculate the loss in gravitational potential energy of the diver. We've got the mass of the diver. So what we want to do is calculate the change in GP. So 65 times by 9.81. Now normally I'd multiply this by minus 54 because you're going downwards, but it says calculate the loss, so I put it in as plus 54 to calculate the loss. And we do that, it comes out as 3.44 times 10 to the fourth, or that's going to be 3.4 times 10 to the power of 4 joules there, as your answer to 2 sig figs, which would be appropriate. Calculate the vertical velocity of the diver at the instant before it enters the water, ignoring the effects of air resistance. So if there's no air resistance, the conservation of energy expression is that the initial GP is going to be equal to the final kinetic energy, because it starts with no kinetic energy, and we're going to use the bottom as our zero GPE line. So what we can do then is equate half mv squared is the GPE, and we've calculated the GPE already. So if we want the velocity, we're going to multiply GP by 2, because we're going to get rid of the half, divide by the mass, and square root. So if we do that, so we take our answer to the previous question, times by 2, divide by 65, square root it, we get 32.55, so that's 33 meters per second, to 2 significant figures there. Okay, so calculate the time taken for the diver to fall 54 meters. So let's write out our motion section. So displacement is minus 54. Ooh. The initial velocity is 0. Final velocity is 32.55. Acceleration is minus 9.81 because it's accelerating downwards. 81, and the t is what we're trying to find. So because we own 4 of them here, we can actually use a range of different equations. So I'm going to use the simplest one that applies here, which I'm going to pick v equals u plus at. The reason I picked that is because u is 0, so time is going to be the final velocity divided by the acceleration. So the final velocity is actually minus 32.55 because it's downwards. So actually let's fix that in there. So that's actually minus, because I'm using upwards as positive. So these are all downwards, they're all negative. I could make them all positive by using the downward direction as positive. So just to explain what I'm doing, I'm using upwards as positive, which is convention. And when we do that, we get minus 32.55 divided by minus 9.81. So you can see the sign actually doesn't matter because they cancel anyway. When we do that, we get 3.318, or 3.3 to 2 significant figures. And because g is roughly 10, you'd expect it to be around 3.3 because it's 33 over 10, basically. Okay, so let's move on to part D. Explain with reference to energy why the velocity of the diver is independent of his mass if air resistance is insignificant. So in terms of conservation and energy, what we are applying is that essentially the initial GPE is equal to the final kinetic energy, because it has no kinetic energy to start with and no GPE at end, and there's no work done against air resistance to introduce another term. So that's the general expression. So what that means is that mg times the initial height is half m the final velocity squared. So you can see here mass will cancel out and have no effect on the final velocity there. So let's put that into words, what we're doing. Okay, so what we've got there is all the initial GP is transferred to kinetic energy because there's no work done at their resistance. So conservation of energy would tell you that. You can see the equation, the masses cancel out, and it leaves us an expression for velocity that's independent of mass or doesn't have mass in it. So that would complete question 1. So let's move on to question 2. Alrighty, so we've got a snowboarder sliding down a slope. So what I'm already thinking is we're going to end up resolving parallel and perpendicular to the slope probably. Between B and C, her acceleration is uniform, so that's this distance here. And we're on a 25-degree slope, you can see here. So the snowboarder travels 1.5 meters from B to C in a time of 0.43 seconds. Her velocity down the slope at C, or final velocity, is 5. Calculate her velocity at B. So let's put in our motion. So our displacement, I'm going to use down the slope as the positive direction. So displacement is 1.5 meters. The initial velocity is what we're trying to find. At C, we know it's going at 5.5 meters per second down the slope. A, we don't know. We could actually work it out, but we don't currently know it. And time is 0.43 seconds. Okay, so that's the information we have to solve this question. So we need the equation that doesn't have acceleration in it. So what we're going to do is we're going to use this one right here. So we can't cancel anything out because we don't know anything is 0, as we often would. So what we're going to do is rearrange this to make u the subject. So multiply everything by 2, divide everything by t, and then subtract v. So we're going to have 2s over t minus v is equal to u there. So we can now plug some numbers in. So u is 2s, so that's 3 divided by the time, 0.43, subtract 5, and when we put that into the old calculator, we end up with 1.98. So an appropriate number of snipping is to give it to would be 2. So it's going to be 2. I just made that worse. 2.0 meters per second. Okay, so the combined mass of the snowboarder and the snowboard is 75 kilograms, and the angle of the slope is 25 degrees. Calculate the component of the weight acting down the slope, which means down parallel to the slope. So if we have the angle to the horizontal, the parallel component is the sine. So the force we're looking for is the weight force times the sine of the angle, which in this case, whoa, is 25. So the weight, we've got the total mass, turn that into a weight force, multiply that by the sine of the angle to the horizontal. That's what we've got here. That comes out as 310.94. So that would be 3.1 times 10 to the 2 newtons overall there to 2 sig figs. Okay. At D, the snowboarder has reached a constant velocity. She moves a distance of 2 meters at constant velocity between D and E. Calculate the work done against resistive forces as she moves from D to E. So if she's going at constant velocity, that means the resultant force acting on the snowboarder is 0, which means resistive forces are equal to the component of weight force accelerating, so the component parallel to the slope. So we just calculated that. So what we can do is use this equation. Sometimes you'll see it with a cosine theta, but they're both parallel to the slope, so they're in the same direction. So this was, if we get that number up, we had a value we calculated in the last question of it's like 310.94. and we're going to multiply out a distance, which we can see from the diagram. Oh, blimey, what's going on with my pen? We can see from the diagram is 2, and when we do that, we get an answer of like 622 blah 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 blah. So that's going to be 6.2 times 10 to the 2 joules there. It's 2 sig figs. State and explain what happens to the gravitational potential energy lost between D and E. So if it's going at constant speed, we know it's not being transferred to kinetic energy. So it must be being transferred by the resistive forces, which means it's being transferred into thermal energy, and that the resistive forces might be friction from the slope or air resistance, something like that. But we get no extra GP during that part. Okay, and that's what we've got written there. So that would be your answer. Okay, so let's move on to question numero 3. All right, so we're going to look at some moments. So the first thing you want to do is state the principle of moments, and what that means is talking about moments in equilibrium. So for moments to be in equilibrium, the sum of all the clockwise moments must be equal to the sum of all the anti-clockwise moments about any given point on the object for it to be in equilibrium. So let's write that down. And when it says any point, it means any point. So you can take moments about anywhere. It doesn't have to be on the object. We can take it in another galaxy, the end of the universe, whatever. If something's in rotational equilibrium, it doesn't matter what point you pick, it will be in equilibrium. All right. We've got a bicycle brake lever, so that's going to be using this principle of moments, and we've got a 35 Newton force to actually apply the brake, and then we've got some distances involved here. Okay, so what I want to do is calculate the moment of the force applied by the cyclist about the pivot, stating an appropriate unit. So a moment is a force times perpendicular distance. So you can see the force is acting vertically down, so we want a horizontal distance. So it's going to be this 110 millimeters. Okay, so moment is force times the perpendicular distance from the line of action of the force to the pivot. So the force is 35, the distance is 110 millimeters. So when we multiply that out, we get 3.85 odd. So we're going to write that as 3.9. And the unit is Newton meters because it's a force times a distance. So let's carry on. Calculate the tension in the brake cable. So I'm just going to flip back and have a look at what it's talking about. I'm guessing it's going to be the force at the moment keeping this one in equilibrium. And it is, because when we hold down the brake lever then becomes fixed, so the moments must equal each other. So the moment from the tension must cancel out the moment of the force. We've just calculated the moment of the force, so the actual tension force is going to be the moment of the force we've calculated earlier divided by the perpendicular distance for the tension. So it's 3.85 was the moment, unrounded. The distance for the tension is 25 millimeters, so 25 times 10 to the minus 3. And when we calculate that, what we get is 0.15 times 10 to the 3, so essentially 154. So the two significant figures, that would be 1.5 times 10 to the 2 newtons. In order to maintain a constant velocity of 15 meters per second downhill, the cyclist applies the brake. The power developed by the braking force is 2.8 kilowatts. Calculate the total frictional force between the brake blocks and the wheel rim. So what you should know is you have this equation. Power is F V. Whoa! It's going to be crazy. So we've got the power developed by the braking force, we've got the speed, so we can calculate what the force of the brake force is. So power divided by velocity, so it's 2.8 kilowatts, or 2,800 watts. It's not my day today. There we go. Finally got there. Divided by 15, and once we do that, we end up with a value of 186.7, so that's going to be 1.9 times 10 to the 2. There is 190 there. All right, so that finishes question 3. Okay, so we've got another mechanics question. They really went heavy on the mechanics in this paper, it seems. So we've got a tower crane with 2 identical steel cables. The length of each steel cable is 35 meters. Each cable has a mass of 4.8 kilograms per meter. Calculate the weight of a 35 meter length. So the mass is going to be 35 meters times the mass per meter. So the weight force, that wasn't even my pen going crazy, that was just me being a nutter. So weight force is mg, so that's going to be equal to 35 times 4.8 times 1 times 9.81. I got confused with my g's there, just 4.8, I don't know why I added a 1 there. Multiply all those together and we get a value of 1648, so that's going to be 1.6 times 10 to the 3 newtons. The cables would break if the crane attempted to lift a load of 1.5 times 10 to the 6 or more. Calculate the braking stress of one cable, and we've got its cross-sectional area. So the first thing is, told you in the question, there are 2 cables, so the load's going to be shared between the 2 first off. So stress is the load divided by area. So we've got the load is 1.5 times 10 to the 6, but it's shared between 2, so it's divided by 2. I've got an area of 6.2 times 10 to the minus 4 meters squared, and once we do that, we end up with a value of 1.21 blah, blah, blah times 10 to the 9. So to 2SF, that's 1.2 times 10 to the 9 pascals or newtons per meter squared. Okay, let's carry on. When the crane supports a load, each cable experiences a stress of 400 megapascals. Each cable obeys Hooke's law. Ignore the weight of the cables. We've got a Young modulus. Calculate the weight of the load. Okay, so to get the force, we're going to do the stress times by the area. So we've got a stress. It was 400 megapascals. So that's 400 times 10 to the 6. We have the area from the previous question times 10 to the minus 4. So when we calculate that, that gives us a value of 248,000. So that's just the force on one of them. So the total force is going to be double that, because that's the stress on each of them. So that ends up being 496,000. So that's going to be 5.0 times 10 to the 5, giving it to 2 significant figures there. Okay, so the unstretched length of each cable is 35. Calculate the extension. So Young modulus is stress over strain. Stress is force divided by area. Strain is extension divided by original length. So if we want the extension, we can just basically swap extension and Young modulus, because we multiply both sides by extension, divide both sides by Young modulus. So let's put in the numbers. So we've got the load. It was going to be half of that one. So what was it? 248,000. We've got times 35. We've got the area. And I think we were just given the Young modulus, so 2.1 times 10 to the 11. And when we do that calculation, we get like 6.6666 times 10 to the minus 2. So that's going to be 6.7 times 10 to the minus 2 meters, or 6.7 centimeters, effectively there. Okay, so next part, this is a lengthy question. Calculate the combined stiffness constant for the two cables. So first of all, we can do it for each one. We need to solve what K is, like this. So we know what the load is, we now know what the extension is. So we can get the spring constant, F over X, so that was 248,000 divided by the extension, so 6.66 times 10 to the minus 2. That gives us the spring constant of just one of them, so let's call that K1. And because they're acting in parallel, the total spring constant is essentially double that, because they're two identical ones. So that comes out as a value of 7.44 times 10 to the 6. So that's just going to be 7.4 times 10 to the 6 there. Okay, so then last part, calculate the total energy stored in both stretch cables. So energy stored, well, we can calculate the work done to stretch them, and if we're assuming there's no lost energy, that's the same as the energy stored. So let's use half F X. So that's half times by the force acting to extend it, which is 49600, times 6.66, which is the extension, times 10 to the minus 2, which gives us a value of 1.65 times 10 to the 4. So that's going to be, actually, it's 1.64 blah blah blah, so that's just going to be 1.6 times 10 to the 4 joules. And that completes this question on the materials. Let's go on to question 5. All right, so we are looking at a optical fiber used for communications, and we can see we're dealing with when the light first enters the optical fiber. And we've got some angles of incidence, and we've got an angle of refraction for the entry, so that's here and here. And then we've got a point where we're going to need it to be reflected for it to work as an optical fiber. Okay, so first thing I want to do is show the refractive index of the core is 1.47. So we're going to do this using Snell's law. Sine I is N2 sine R. It's going from air, so that's N1 is equal to 1. So N2 is just sine I over sine R. So the angle of incidence, 14.1. Angle of refraction, sine of 9.54. And that's going to give us a final value. When we plug that in, do the calculation, and it's going to come out as 1.4699, so 1.4 699. I wouldn't normally show all these figures, but we are doing a show that question, so I'm going to show it all unrounded, and then we see that that's 1.47 to 3 sig figs, which is appropriate as the data was all 3 sig figs. The refracted ray meets the core cladding boundary at an angle exactly equal to the critical angle. Complete figure 4 to show what happens after it strikes the boundary. So at the critical angle, the refracted ray just goes along the boundary. So that's what you can see there, it going along the boundary. It's a little bit more wiggly than I intended, but it's supposed to go straight along the boundary. It wants us to calculate what the critical angle is. So we've got the refractive index of the core. Do we have the refractive index of the cladding? No, we don't, but we can, from the diagram, work out what the angle is. So I'm going to create a right angled triangle here. This is the angle of incidence, which must be the critical angle. So actually it's going to be 90 minus 9.54 there. So it's going to be 90. Well, it's actually 180 minus 90 minus 9.54, but we can hopefully fairly straightforward. And you see that we can get rid of the 90s. When we do that, that comes out as 80.46 or 80.5 degrees there. This 90 is an integer, so that's an infinite number of significant figures. So we would give the answer to 3 significant figures would be appropriate here. Then it wants us to get the refractive index of the cladding. So under the conditions of total, the critical angle, sorry, sine of the critical angle, that's just equal to N2 because the angle of refraction is 90. We just got the angle of, we've just calculated the critical angle. We know what the refractive index of the core is, which is N1, so it's 1.46 blah blah times by sine of 80.46, and once we put those into the calculator, what we get is like 1.4496, so that's 1.45 there, which seems reasonable because it's smaller than the refractive index of the core, which is good because it needs to go from high to low optical density, so that checks out, but it's still higher than air, so it seems very reasonable. State 2 reasons why optical fibers used for communications have cladding. So one thing would be to protect the glass in the middle from scratches and breaking. That helps, and you can also use it to increase the critical angle, so that's quite useful as well. So that's quite a useful thing, and also it would stop signals going from other optical fibers. So if you had just the loads of glass next to each other, you might get signals hopping around. So any of those would be good here. Okay, so that's that one. Those of you wondering how it increases the critical angle, it does it because essentially it's going to change this value. So if it was just air outside, this would become 1. That would then change what the critical angle is, and you can try that out and you'll see the critical angle is actually increased by adding something with a higher optical index than air. Okay, so that finishes question 5. So question 6 is a longer answer type question, and it wants us to discuss the formation of stationary waves on a string or rope. Your account should include a labeled diagram of a stationary wave, the conditions necessary for a stationary wave to form, and a definition of the terms node, antinode, and explanation of how they form. Okay, so this is a very, very friendly 6-marker question, which is incredibly annoying for those of you who've worked hard and prepared yourself, because this is very easy, but nevertheless, we've still got to get it done. So what we're going to do is we're going to have, we're going to have a fixed end over here, and we're going to have an end that is free to oscillate up and down. So let's show that essentially this end is oscillating in that direction. And then let's do a, oh blimey, we're going to do a first overtone here, so that's where we can see a full wavelength. We've got nodes here, 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 and antinodes here and here. That's our stationary wave. So let's just label our diagram a little bit so it's clear what we're showing. So we've got a fixed end. We've got an oscillator at that location, and let's label a few features. So we've got an antinodes, and where are those? Let's indicate those in our diagram. So you've got one there, you've got one there, and we've also got some nodes, and let's indicate where those are. We've got one there, and we've got one right over there. So that's generally the setup. So that's our labeled diagram of a stationary wave. Let's now explain how they form and what the different terminology means and where they come from. So the first thing is we're going to discuss the conditions required. So we need two progressive waves traveling in opposite directions at the same speed, same frequency, and a similar amplitude. So those are our conditions for them to form. Alright, so those are our conditions to actually get a stationary wave. Do we have those conditions here? Yes, we do, because one progressive wave goes from left to right, reflects off the fixed end, and as long as it doesn't lose too much energy in the reflection, those conditions are going to be satisfied. Alright, so that's what I've explained there, how we actually end up with the right conditions. So I also wanted to explain what a node and antinode are and how they're formed. So let's do that. So a node is a part of a stationary wave with zero displacement, and it forms when the two progressive waves meet in antiphase and destructive interference occurs. Antinodes are the opposite. They're regions of maximum displacement. So that's where the two progressive waves met in phase and constructive interference happens. So nodes, destructive, antinodes, constructive. Okay, so let's get that down. All right, so that's what we've got there. One thing I'd just like to draw your attention into at this point is that I've made a specific point to mention superposition as part of my answer, and then again up here. I think AQA has a sponsorship deal with some sort of company called Superposing, because in the mark schemes they always give a mark for saying the two waves superposed. So get it in your answer. It's like handing out a free mark every time they do stationary waves. Okay, so let's then move on to question 7. Okay, so we've got paths of a microwave from two narrow slits acting as coherent sources. So that's what we can see here. So here are your slits that form a coherent source, and then here is like with light, this is like where your screen is. We've got a detector to detect microwaves instead, because obviously you can't see them. That's pretty much, so it's basically the same as a Young's slits. Explain what is meant by coherent sources. So it's sources with a fixed phase difference. And you achieve that by having the same frequency or wavelength. It's light, so we know they have the same speed. All right. Okay, so that's what we've got there. So those of you wondering, well, normally when you're defining a coherent source, you just say sources with a fixed phase difference. Yes, you would, but what told me to give some more information is the fact that this question is worth 2 marks, and there's no way that statement there is worth 2 marks. So I just added in an extra detail to earn that second mark there. Okay. So the frequency of the microwaves is 9.4 gigahertz. Calculate the wavelength. So microwaves are electromagnetic waves, so they travel at the speed of light. So your wave equation has a c in it. We want the wavelength. So it's c over f. So that's 3 times 10 to the 8 divided by 9.4 times 10 to the 9, because it's in gigahertz. And when we do that, we end up with a wavelength of 9.19 times 10 to the minus 2. So that's going to be, should I say 9? Sorry, 3.19. So that's going to be 3.2 times 10 to the minus 2 meters or 3.2 centimeters there, which seems quite long compared to all the wavelengths you're usually getting with these questions, but these are microwaves, so they're up towards the radio end of the spectrum, so they do start to get into this sort of scale. Okay, so using figure 5 and your answer, calculate the path difference between the two waves arriving at the detector. So I'm going to flip back and have a look at the diagram to see what we're looking at. Okay, so looking at the diagram, you can see from the slit on the left-hand side, there are 6 wavelengths between the slit and the detector. On the one on the right, there are only 5. So there's a path difference of 1 wavelength. So that's just going to be our answer to the previous question, 3.2 times 10 to the minus 2. So it's going to be an area and maximum is formed because the path difference is an integer multiple of the wavelength. Oh, I've actually answered this question. So let's put that down. So what we've got there is the path difference is an integer multiple wavelength. That actually is 1 times the wavelength. So constructive interference is going to happen because they're in phase with each other. So a maximum is going to be formed. Okay, so the experiment is now rearranged so that the perpendicular distance is now 0.42 meters. The fringe spacing now changes to 0.11 meters. Calculate the slit separation. So for a double slit, your equation for the spacing is lambda d over s. And it wants the slit separation, which is s. So we can swap s and w essentially. D over s. So that's 3.19 blah blah times 10 to the minus 2. The screen distance is now 0.42. Spacing is 0.11. We plug that in, we get 0.1218, so 0.12 meters is the slit spacing. And if we think about the value we got previously, it's about an order of 10 out of the wavelength, so you could get some diffraction happening there. And for this question, 2 sig figs would be appropriate because these values you were given in the question are 2 sig figs. With a detector at the position of a maximum, the frequency of the microwaves is now doubled. State and explain what would now be detected by the detector in the same position. So you would still find a maximum because on the left we had 6 wavelengths before, so we've got 12, and on the right we had 5 wavelengths before, so now we've got 10 because we've doubled the frequency. So the path difference is now 2 wavelengths. So you've still got it as an integer multiple of wavelengths, so you're still going to get constructive interference, so you're still going to get a maximum. So that's what we've got there. It wouldn't actually change what you're detecting at all. So that finishes off this question paper. I hope you found this video useful to clear up any issues you might have had on this paper. If you've seen any errors or things that are not clear, please do let me know and I'll help you out with that. So just comment below the video and let me know. But make sure you check out the other playlists I've got. So on Unit 1, Unit 4 and 5 to help you with all the different topics in AQA physics. But thank you for taking the time to watch and I hope to see you again.